So this topic is predictive maintenance. It's a little bit of a side topic from anything that deals with EAM directly. Oftentimes integrating the softwares for predictive maintenance into your EAM system are not as clean. There's a lot of proprietary software on the PdM space, and so you're better off dumping things into a data lake and using your reporting capabilities from there. Although you would use EAM for things like creating the work orders for those routes to collect that information. So this particular presentation is actually going to focus on the technologies themselves and what their use cases are so that you can use them as part of your preventive and predictive maintenance plan within EAM. So what exactly is predictive maintenance or condition monitoring? So it's basically a technique where we are monitoring the condition of an asset, whether it is online or offline, for signs of degradation. We're attempting to look at an asset versus its baseline to see whether we're using technologies like vibration analysis or ultrasound. What we're attempting to do is compare a baseline to a new reading to see if we can determine deterioration and write a work order to replace components. The reason we're doing that is to give us optimal window time to plan, schedule, and execute the work. So various techniques, we're going to go over a few of these today, not all of them, we don't necessarily have the time. Vibration monitoring, ultrasonics, tribology, which is oil analysis, performance testing. So performance testing is something like looking at your pumps against the pump curve and determining whether or not they're still efficient or whether or not you need to replace the impeller. Visual inspections, infrared thermography, motion amplification. We'll also take a brief look at electrical signature analysis. So why do we use predictive maintenance? Well, we use predictive maintenance, again, to give us the largest window of opportunity to plan and schedule work with minimal ancillary damage. So oftentimes, if a bearing in a pillow block is going to foul, when it fouls and it blows apart, we score the shaft. And then we have to replace the shaft and the pillow block and the bearing. In order to eliminate that extra damage and all that extra cost and the rush order of parts, we utilize predictive technologies to see that degradation and replace the component when it's convenient for the operation. Not that it's ever convenient for the operation. When it is the most convenient for the operation. This is not a substitution for sound inspections. A good PM program is designed to assess and inspect your equipment. Predictive technology is not going to see necessarily a cracked foot on the conveyor. It will on things like a pump. It's also not a crystal ball. It's not always 100%. You can still have a random event failure when utilizing predictive technologies. It's absolutely worthless if the analysis is not turned into a work order. If you get the vibration readings back and it says that we have a pump that's going bad and we need to replace a pump bearing, and operations goes, yeah, I don't believe any of that hocus pocus mumbo jumbo. I walked past it and there's no problem. I can't smell it, feel it, hear it. So you can't have the asset. And then we have the catastrophic event. The predictive maintenance didn't do a lot. And predictive maintenance is part of your strategy. It's not a program. It's part of your maintenance strategy. It's how you assess for condition. So let's walk through this one more time. This time we'll actually take some detail to it. For those of you that were here during the kickoff, you may have seen this. So assets foul in one of three phases, either in early wear out, like their warranty conditions, they weren't installed with precision. We installed the bearing, but we forgot to pack it with grease. I'm sure we've experienced that. They're early wear outs or infant mortality. On the far right-hand side is a unicorn. That's when an asset actually lasts its useful life. That's a pretty rare event. And then in between is everything else. And everything else is random because, well, if I turn two assets on at the same time, they don't fail at the same time. The probability is extremely low. Those assets are designed with a base condition. How much you will spend to operate and maintain them is baked into their engineering design. We used the example yesterday of a Yugo versus a Corolla. Your maintenance and operating cost is baked into it. You don't really get a choice. Once the asset shows up at the plant and is installed, the budget for it is a known entity. You may not actually know it, but it's baked in. The maintenance organization and use of predictive technologies is designed to see and mitigate degradation. So across that baseline and over time, an asset begins to deteriorate. The maintenance organization lubricates it, replaces belts, inspects things to bring it back to base condition. When they're finished that work order, it should be back to base condition. If immediately after that PM they have to show up because they put stuff in wrong, that's rework. We begin to deteriorate again. Maintenance does an inspection, replaces wear components. This happens over and over and over throughout the life of an asset. The inverse of that deterioration is a cost that goes up. And so as we deteriorate, our cost goes up. If my impeller is wearing, the VFD has to ramp up to keep up flow and pressure. That costs energy. If I don't lubricate my bearings properly, I increase friction. That costs energy. So my costs keep going up, and then I restore to base condition, and they come back down to the base cost to operate and maintain the asset. We utilize reliability and asset management techniques, such as designing things for reliability, reliability-centered maintenance, and FMEA. If anybody saw the presentation, it was in this room previously. We use those techniques to alter where the baseline is. And when we alter where the baseline is, we also impact its rate of deterioration. Because believe it or not, one of the things an asset doesn't like is to be touched. It just wants to run. So if we PM things too often and we do a bunch of extra work just because we're there, oftentimes we're doing damage to the asset. We're not helping the asset. Usually, the lowest frequency visit to an asset is due to its lubrication requirement. So most rotating assets that require lubrication, we go to at some frequency, whether it's monthly or quarterly, depending on the bearing in the asset. And then we have this long task list of stuff to do just because we're there. And it doesn't really need that. And so when we use the FMEA process, we change those things and we end up with a different baseline. But eventually that asset is going to fail. And the predictive technologies that we're going to go over today are designed to help find those failures before they are catastrophic. It gives us a maximum planning window. It allows us to know that that asset is going to fail and what the component is that's going to fail, allows us to properly order it, allows us to get to a closer just-in-time inventory. I don't need to stock it if I know it's going to fail ahead of time, as long as that window is bigger than its lead time, which today just keeps growing and growing, right? If I wait until my senses can pick it up, it's too late. At that point, I'm rush ordering parts if I don't have the parts. And my costs go up. My costs go up for two reasons. The costs go up because I'm rush ordering parts, but also because there's ancillary damage. There's other components that fail. So if we want to get our maintenance costs down and actually make an impact, the use of predictive technology is a great way to go. You do not have to have catastrophic events. You do not have to be a reactive maintenance organization. There are ways out of that. And these technologies are one of those ways. If we look at and think about the presentation that was just prior to mine, and we go through the FMEA process, the second question we ask when it comes to a failure mode that has a high risk priority number is, can I assess its condition? The first question we ask is, can I engineer it out? Can I make the failure go away? If I cannot do that, the second question is, can I predict it? Can I assess for this condition? And that's what we utilize these tools for. The first one is vibration monitoring. And vibration monitoring can be utilized on pretty much anything that rotates. If it rotates, vibration monitoring can monitor it. If we consider a shaft and a keyway on a shaft, and I roll the shaft on the floor, the keyway will make this sinusoidal wave. Does everybody follow that? Great. This is called 1 times turning speed, or 1 cycle, or 1 order of turning speed. If that shaft has 4 fan blades on it, every time I rotate the shaft, there are 4 sinusoidal waves that occur, 1 for each blade. And they are considered phase locked, meaning they're locked to the shaft. And in this case, because there are 4 and they are equidistant, they are 90 degrees apart. If I have a gear with 12 teeth on that shaft, it has 12 sinusoidal waves. Vibration monitoring takes all of that information and combines it into this incredibly clear picture. It's not called a time waveform. And that time waveform looks like this. And there are some people really smart enough to analyze this. I am not one of those. And so the software associated with vibration analysis does a mathematical computation called a fast Fourier transformation. That fast Fourier transformation basically takes this time waveform and looks at it sideways. And when I look at it sideways, what I get are just some peaks. I get peaks at 1 times turning speed, at 4 times turning speed, and at 12 times turning speed. And I can see the amplitude of those peaks and how those peaks are interrelated. And vibration analysis simply takes a look at those peaks and makes some determinations. For example, a belt frequency is less than turning speed. So if I have a high peak at below 1 times turning speed, there's a really good chance I have a belt issue. If I have high 1 times, 2 times, 3 times, 4 times in a row, that's a really high probability I have mechanical looseness. And I'm just doing this. And so vibration analysis uses this data to assess a lot of things, including bearings. Bearings are a whole different analysis set. We're not going to get into the technical stuff on that, but here's the gist of all this. Like anything else, a trend line is your best friend. I don't need to know anything about vibration analysis to know when I started having a problem in this chart. I see the problem, I just need to know what part to replace. Now you're all experts in vibration analysis. No. Next up is tribology. Tribology is the science of friction. It's about surface wear and friction. When we lubricate a bearing, the grease that goes into the bearing becomes a liquid and creates a small oil bath. Hopefully it's a small oil bath. If you're filling up your bearings till grease is spewing out of the seals, you're actually doing a lot of damage because there's no room for the oil bath. That oil bath creates a coating around the spherical elements or roller elements and the inner and outer race of the bearing, which allows them to run smoothly. And they continue to go out of the oil bath and back in the oil bath over and over and over again. Tribology looks at 2 major factors. It looks at whether or not the lubrication still has its lubricating properties, which means, is the lubricant particle still good enough to create a film thickness around the roller element? The other part of the analysis is what's in the oil that shouldn't be. So if I have a gearbox and I take an oil sample and there's a bunch of brass in my sample, they didn't ship me free brass with the lubricant. It's not supposed to be there. That means I have gear meshing. If there's water particles in my oil, that's actually a bad thing. So it looks at what concentration of different particles in parts per million exist, which ones should not be there, and it looks at the properties of the oil itself and whether or not it can still do its job. And this is an incredibly inexpensive way to do two things. One, save you a ton of money in hydraulic oil replacements. A ton of money. And two, tell you when you should actually replace it. If you have a lot of hydraulic, I know some folks in here were in injection molding and stuff like that. If you're taking oil samples, you will save a ton of money. You want to improve reliability? Look, reliability in rotating plant and rotating equipment comes from two things. You do two things really well, and you're going to do fantastic in maintenance. One, lubricate properly. Don't over-lubricate, don't under-lubricate. Get an MLT1 certification, maintenance lubrication technician certification, and learn what lubrication is all about. Because filtering your oil matters dramatically. The second thing is learn how to install stuff with precision. Use laser alignment tools, learn how to take clearances out of bearings, get training in precision installation. Because most failures, early failures that happen during the random period are because we didn't install it right or we don't lubricate it right. Let's look at infrared thermography. How many people are using infrared thermography? 1, 2, 3, 4. Infrared thermography can look at your electrical equipment. That's pretty straightforward. We'll look at what the technology is in a minute. But it can also do an awful lot of other things. It can look at things like rooftops and see insulation degradation. Asphalt paving, so when they lay asphalt down, if you've ever driven down the road and you see that alligator pattern in the center right after they laid it all down, that's because there was a cold spot in the truck. And that area cooled down faster than the rest of it. So they had a lump of asphalt in the center of the truck that was colder than the rest of it, and so it shrunk faster. You can pick that up while they're laying it and tell your vendor, because they have to drive that truck with the hot asphalt from wherever it is they put it in the dump truck to your place. And the entire time it's cooling. Building envelopes, you can look at energy loss around building envelopes. From a medical perspective, they're now using this technology to determine melanoma. Obviously, in airport security, they're using this technology during COVID as well. And we've all seen amazing military videos using infrared technology. It's predicated on the fact that all things above 0 Kelvin emit infrared energy. The camera cannot see heat. It detects infrared radiation being emitted by an object. That emission of infrared radiation is determined by two factors. One, the temperature of the object, and two, its emissivity value. Emissivity is how well it emits infrared radiation. Some objects emit it very poorly. Some objects emit it very well. Does anybody have low E glass in their home? It doesn't mean low energy cost. It means low emissivity. The glass doesn't emit. It doesn't project out infrared radiation. It's coated so that it has a poor emissivity. Has anybody been to, let's see, anybody, I guess, in brewing? Anybody in beer, wine, anything that fermenting tanks? There's a reason why they're polished and shiny metal. They don't have to insulate them because polished shiny metal is a very poor emissivity. And you can get very close to those tanks without feeling the heat. It's so they don't have to spend money on a bunch of insulation. It's not so when you walk through, you go, wow, that's so cool, those copper tanks. They're shiny. They're shiny for a reason. They don't emit infrared radiation, so they don't lose their heat. If you have pots and pans at home, and some of them are stainless steel and some of them are painted, coated, boil water into two of them and see how close you can get your hand to them. The one that's shiny, you'll get much closer to before you feel the heat because it's not emitting infrared radiation. So this camera sees that infrared radiation. Interestingly enough, you can get an infrared camera in your technician's hands for about $400. You can get a FLIR one right on Amazon for $400 for the Pro version. The regular version is $300. That's inexpensive. How many people have PMs that say check connection? How do you think they check the connection? How do they do it? They tug on it. What's one of the worst things you can do to an electrical connection? Over torque it. You're creating looseness. You're creating the failure by physically checking the connection because it's very unlikely that they're using a torque screwdriver. Hopefully they are, but the probability is pretty low. I can look at the same electrical cabinet, open the panel, use my infrared camera, shut the door, I'm done. Did I have loose connection or not? Which one of these has a loose connection? If I'm a mechanic, I'm an electrician at your plant, and you gave me the PM task to go check my electrical connections, which one is it? I don't know, but if you put an infrared camera in my hand, it's pretty straightforward. It's that obvious. Both of these pumps are running. Which one has a problem? I don't know, but now I do. It's that simple. An infrared camera will pick up rotor bar issues, hot bearings, anything with a delta T. I use it to check my propane level in the grill at the house because it really is that obvious. I used it when I bought my house to check the building envelope, see if there was any problems. True story. In like 2003, 2004, I worked for a large pharmaceutical company, and I was responsible for predictive technologies across a bunch of sites. And they wanted to do a flyover with an infrared camera to see if they had roof insulation problems at 5 different R&D sites, hundreds of buildings, acres of land, 5 different sites in New Jersey. So we looked up pricing to get something to fly over that had an infrared camera already mounted on it, and the price was outrageous. So I said to my boss, I'll do it. He said, what do you mean you'll do it? I said, well, we'll just rent a helicopter. I'll go up in a helicopter. So we rented a helicopter. You have to take the door off because it can't see through plastic. At that point, I started rethinking my volunteering. And back then, an infrared camera didn't record video, so we had to buy like a separate DVR, hook connections up to it. And interestingly enough, did you know that inside a helicopter, it doesn't have a shoulder strap, it's just the waist strap? I also didn't know that until I was ready to take off. And I went, what do you mean? Like, that's it? That's all I got? And they were like, well, that's all that's in the helicopter. I mean, you took the door off, what are you gonna do? So we flew over central New Jersey in a helicopter at 1,000 feet, and I hung out of the helicopter, true story, and I held this thing in my hand, which I should have brought a glove. I wasn't thinking at all, because I was freezing the whole time. Hanging out of a helicopter taking pictures. This particular building is Building 109 at one of our sites, and it houses Clinical Supply Pharmaceuticals, and it's about to have a roof leak. That's a significant loss. These are like the test drugs before they actually go to market in this building. And what you see here is all roof insulation problems. All those light areas. So what happens is water infiltrates the roof. And if it's hot out during that day and nice and sunny after it rains, so you want it to rain one day and be nice and warm and sunny the next day. The rest of the roof dries and gets dries easily. The insulation stays wet. At night, the roof cools down really fast where it's not wet. The stuff that heated up all day and was wet stays hot longer. So you take the helicopter up, you fly over the rooftops, and all these hotter areas are insulation problems. and we wrote a capital project to replace the roof and got that done before we destroyed a clinical supply area. Another interesting story. We have an underground water leak that we don't know where it is. I get a phone call that says, hey, George, I need you to check something out. There's a boiler feed pump problem or boiler water makeup problem because it's going through the roof. Well, what do you mean your boiler makeup water's going through the roof? Well, we don't know. We're not getting the same amount of condensate back. I got to figure out where the leak is. This is a 400-acre campus with 35 buildings fed from one central utility plant. How do you find the leak? You would be drilling a lot of test holes that cost $15,000 to $20,000 a piece at every fitting, at every thrust block, everywhere, right? We used an infrared camera, walked around at the rooftops. We found out that it was 40 degrees outside and the asphalt where this gentleman is standing is 80 degrees. It's not supposed to be 80 degrees. We dug one hole. 14-inch condensate return line. There's the light post he was standing next to. He was standing right here. We dug one hole. Garden hose size leak in a 14-inch condensate return line. That's what happens when they backfill on Saturday. And no one's there to witness it. Pea gravel right to the top. No sand bed. That's huge. That's a ton of money you would have lost trying to find the leak. This is just an example of a breaker, and we used to cut things apart and double check them. Cut bearings apart so you can see whether or not the analysis was right. We cut this breaker apart to make sure we said it was fouling, and sure enough, it was fouling bad. It was arcing at this foot to a point where it would have been a fire. Electrical signature analysis. Anybody using like motor current testing or electrical signature analysis, any of those types of technologies? Okay, so electrical signature analysis is slightly different than motor current testing. Electrical signature analysis can do all of that testing and more from the MCC bucket. You do not have to go to each motor. You can go right to the MCC panel and hit every single motor very quickly through electrical signature analysis. And electrical signature analysis can actually get down to component failure. Unlike just MCA testing, unless it's the winding, it's not really telling you a whole lot. So it takes all of the various tests that you would need different components for, and it can do all of that testing directly at the MCC panel. This is also a great tool if you have added a bunch of VFDs to your plant. If you have added a bunch of VFDs and you're blowing boards on a regular basis, it's likely that you're not filtering your electricity and you have harmonics back to your substation. And this can find that issue. So if you've installed a bunch of VFDs and you're having issues with boards frying, oftentimes it's harmonics back to the sub. So it uses fancy technology that I'm not really that aware of, and it can test all those components right from the MCC bucket. We used to do online and offline motor current testing, but this tool turned out to be way better. Does anybody have like repeat bearing failures on motors that you have VFDs on? No? Okay. If you do, check for fluting. Fluting is a phenomenon where when the VFD reduces energy and slows down the motor, that electricity has to go someplace. So it goes through the stator, arcs across the bearing, and goes to ground. And then it ruins the bearings very fast. And usually in like 90 days, 180 days, you're going through bearings. So if you ever have a VFD-driven component and the bearings foul, take the bearings and wash them. If the roller elements are dull and you see this zebra stripe pattern on the inner and outer race, you're fluting. Motion amplification. Motion amplification is an interesting technology. It's a newer technology. Has anybody seen motion amplification yet? Great, I can lie. You just make this up. No one even knows what it is. So unlike vibration analysis, where you're collecting at various points, motion amplification takes points at everywhere. Because what it's looking at is changes in pixel color on a video. So for example, the camera that's in front of me is fixed to the floor. It's not moving, somebody's not holding it where they're shaking, it's fixed. It knows which pixels in that frame are silver or not silver. Does that make sense? Okay. Because the thing shakes a little, there are pixels that change color. Motion amplification, you can't see it, but because I'm walking, it's changing. Motion amplification simply says, well, if 1 pixel changed silver, make it 4. And now I can visually see the movement. And so things I would not have been able to see in the past, I can now see. Whether it's looseness, pipe strain, cracks in my frames, you'll see, it's scary. Google motion amplification and watch some videos. It's a technology that was derived at MIT, and it's pretty much free. You can actually take any video you want and upload it to MIT's website, and they'll apply motion amplification to it. Not the same as this technology. This is far greater, but it does the same thing. So all the slight variation in pixel changes get excited. And so things you don't think are moving become very visual. And you can see looseness ungodly. Really, really cool technology. Ultrasonics. Ultrasonics is for hearing things that you can't hear. This technology is easy to use, easy to get into the hands of your technicians, and it will pick up air leaks from across the noisy room. Air leaks, steam traps, bearing issues, this technology can be used for all of those things. So in an airborne scenario, it looks for gas leaks, vacuum leaks. It can also pick up electrical corona, arcing, without having to remove the cabinet because it's audible. So you don't have to open up the cabinet to hear arcing or corona. Also good for tank inspections. They have a tone generator. You drop it in the tank, close the tank, you can hear any leaks. From a mechanical inspection standpoint, bearing issues, pump cavitation, steam traps, underground leaks, you can actually get what's called a grease caddy, bolt onto it, and you can do lubrication based on sound. So you listen to the bearing, apply a little bit of grease, hear it get quieter. And if the noise comes back, you don't just keep pumping more grease in. That means the bearing's no good. Performance testing is where we take a baseline and compare it. So if we have a pump curve and I, in the future, take my pressure readings, I can know where I am on the pump curve still and whether or not I need to replace an impeller. This is good for things like heat exchangers, where I should have a specific delta T. I can see whether or not I need to dip my coils because I'm losing efficiency across the heat exchange. So you're just comparing the baseline installation performance to wherever you're at today to see a degradation over time. And that's an example of a pump curve. And it can be used on an awful lot of things, including turbines. It's driven by design to premises. As things degrade, we're going to perform differently. And so we monitor that performance. For all of these predictive technologies, first and foremost, be a skeptic. I don't want you to believe them. I want you to be a skeptic. Go use it. Go see its value. Oftentimes, when the vendor comes out to do their demo, make them do the demo in the plant. You'll find enough problems to pay for the unit, especially if it's infrared and ultrasound. You'll pay for that unit the day they do the demo. Track your cost savings and avoidance. Make sure everything goes inside EAM. All of your collections should be documented in the EAM, and all of the output from the report to go do the work that's repair should also be in EAM. The other thing that you have to do is remove all of the physical intervention tasks from your PM tasks and your task lists that are addressing the same failure mode. If I'm using vibration analysis on my pumps, I know whether or not I'm going to have a coupling failure. I should not have a physical intervention to inspect the couplings. This is where PdM initiatives fail. They don't realize the same benefit. Because when you start using the technology, you now don't need the physical PM. And often places I go, they have the technology, maybe they're using it, hopefully they're using it, but they haven't gone back into EAM to remove the task, the physical intervention that's no longer necessary. And so they're not getting all of the benefit. You should be getting some resource time back. It shouldn't cost you resource time to use these technologies. It's a transfer of resource time. So folks buy the technology and you go, well, I don't have time to use it. Well, I guess not, because you're still out there inspecting the couplings. I encourage you to learn a lot more. Like in a 45-minute presentation, we went through like 6 different technologies. And like this is a 2-day class normally just to do an overview of these technologies. And each one of these is a 4-day class plus an exam to get certified in. So you got a small taste. This was like, you know, the wine tasting. Go learn an awful lot more about predictive technology. Yes, sir.
All right. Well, thank you, George. Appreciate you. And we appreciate all you.